had this signal going out of it, saying, in addition to whatever other input or output it's sending, saying, start the operation, and once it's ready, it's going to read the operation. So it's going to have this start and ready handshake signals, and then these are when it's going to call the slave is going to pass the variable start and ready to that slave. And again, we have a finite state machine which says, once this you want to call this other entity the slave, the start will be 1, and now the slave knows that it has to start operation, and it's going to send data as well. And once it goes to the wait state, and the wait state is basically looking for the ready signal from the slave, which we defined here. So it's connecting the slave to that ready signal. And once this ready signal is asserted, we know that the value of the output is ready. And then at that point, we are going to read the output as it is shown here. And then we are going to repeat the same procedure, just going to that wait state. And once the module is done, we know that we've computed this task twice, and then we are going to do this. So basically, in the handshaking example, we have this few start handshaking which transfers the data. Then we go in the wait state. Whenever this is done, it's going to handshake again, says things are ready. Then this is going to go to wait state compute, so on and so forth. Now, there is more than one style for handshaking. There's the style we just saw where, we had this wait state, which you kind of keep probing in that, every clock saying, are you done? Are you done? The other one is, if we have a fixed count for how much the wait should be, or which could be sometimes an overkill because we may not know always what is how much time it takes, but sometimes we know, so it's an easier, cleaner write style to do that. And then we go to the output which was the idle state at this. Here are two examples of what we have just seen. Here, the wait state is, as we described earlier, it's waiting for the ready signal from the slave until it's ready. Then it's going to stay in the wait state. The other one is when you have a counter, which is going to count, and if that counter reaches a certain state, we know that this is ready, and it's going to get the results. So naturally, the style 1 is easier to write code, but if the completion time of the slave module is variable, this is what is recommended to use. But if we know that exactly this many cycles are going to take for the slave modules to finish, then it's better to have a predictable control flow, and may be able to write better controller, similar to the ALU controller that we've seen in the last lecture. And the thing is, we need to know exactly how many clock cycles each one of these tasks will take. And if the other drawback could be that in the style 2, sometimes if the completion time is variable, we have to do the maximum amount of possible computation before we finish and go back to the master. There are other kind of a little bit more complex scenarios for handshaking. For example, if you have a module slave that is being called or is by other masters, then it may be busy. We may not be able to use the hardware resources. And now, if we assert the start, in the beginning, in the middle, even for the same master, if you assert a start in the middle of a computation, it may mess up the computing. So the slave may have an additional signal which is a busy signal, which says I'm going to ignore every start request coming to me if if I've already accepted another job. And then in addition to the ready signal, we are going to check the status of the busy signal because before we assert a start. And this is of course especially important if we have more than one master module. So here again the same handshaking scenario, but we have one busy signal added to the handshaking scenario. Okay. So far we've seen kind of an example where we called the same module, but we have only one instantiation of it, but we kind of time multiplexed. We had a controller which said, I'm going to use this module twice, but I'm going to use it in different points of time in different states. And we did it either by handshaking or just by designing a controller finite state machine. But there was the combinational case where we only had, there is, remember, the function we are doing is that r equals square root of p plus square root of q. And now we could just go and have this square root of p and square root of q in two different hardware instantiations, and then just do the design like that. Then it's a combinator. You could even do a combinational design for that. And a combinational design, in some senses, it's nice because you only take one clock cycle, so it's faster. But as you see here, in terms of the number of LUTs, this is substantially more output because we are not reusing the output. This is substantially more hardware because we're not reusing the same function. And but here we are storing the values for the first pass of the function before we go to the second pass. So we add to the number of memory elements or flip-flops here, and here in the combinational you could also use the DSP units on the module, which we didn't discuss. But here again you see an example where we have more resources used, but the number of cycles, as you see here, is shorter, so the time is less than the sequential, because in sequential we are adding some control, and we are basically having a longer bit width. So the combinational approach is faster but requires more area. The sequential approach is slower but requires less area. So this is basically a design trade-off. There are, of course, other possibilities how we could design this. We could have this sequential square root module, in other instantiation, and these design decisions are always happening in practical design, and the designer's intelligence is to basically try to choose the best option. The tools are helping us optimize things, but some of these decisions are basically designer decisions, and they cannot be always automated. So the tips for this is basically make sure that each of the submodules or the modules that you have in your design independently work. So design test benches before and try to make sure that the input outputs are behaving correctly before incorporating them. And first design the standalone modules, then add handshaking, and try to write test benches that include all possible scenarios. EC 111, lecture 9, set 6. This is just a super short video, just discussing in a high level the project 2. The description is given in the post. That this byte rotation is important because we are basically learning how to access memory and how to do a little bit transform on the memory and then write back to the memory. That's the significance of this project. You're going to use this operation in the final project and in the projects that we have upcoming. So basically, the byte rotation is just like some simple transform about the content of the memory. The intention is for you to learn the memory model that we will be using for the rest of the projects. Good luck.